Okay, so next under orbits, we're going to look at three extension topics. The first is Kepler's third law. Now, we already proved Kepler's second law, and that was basically from the angular equation, we determined that r squared theta dot was a constant, and then by drawing a triangular shaped wedge, we showed that the rate of area change, the rate at which area was swept out by the orbit, was a half r squared theta dot, and that will therefore be a constant. The constant will just be 1/2 h. Now let's take that result and cross multiply it, and we'll get dA is half of h dt, and then let's integrate that from an initial time of 0 around all the orbit, so the period t, and then initially there'll be no area at the starting point, and we'll arrive eventually at the entire area. This is makes most sense, of course, for an elliptical orbit. And so this works out to the area. This side, of course, is a half h times the period t. So the area of the ellipse ends up being related to the period and the angular momentum constant. Now, a bit of ellipse geometry here. The area of an ellipse can be shown using calculus 2 techniques to be pi AB, where A is the half length of what's called the semi-major axis, and B is the half length of the minor axis. So the entire major axis length from here to here is just 2A. This is twice A. Now, this on our orbit analysis we defined as the distance of closest approach, the perigee distance r0, and then this was the apogee distance rf. And A is going to be, you could see that twice A is r0 plus rf, and then we could just divide by 2, so that A is basically the average of those two. Now, in terms of the eccentricity, you can show, using the definition of ellipse, that the B and the A are related through the eccentricity. So we can substitute in that value, which again comes from conic section math, in for the B, and you get this for the area of the ellipse. Now we're going to substitute that into our previous relation for the period. So we'll get 2 over h times, and then substituting for the area, pi a squared root of 1 minus epsilon squared. So this is pi AB. There we go. So you put, for B, you put a times the square root. When you put in a times the square root, you get a squared times the square root. So that's where we are right now. Now we're going to square both sides. So period squared is 4 pi squared over h squared times a to the 4th times 1 minus epsilon squared. Now, we're going to use the definition, or rather the solution to the differential equation for the orbit as a function of theta, the eccentricity definition, and the definition of B to show this result here. The way that we're going to do that is we're going to take the at the perigee, that's going to be at an angle of 0, and the cos of 0 is just 1. So this is A plus B, but then A is epsilon times B, and then of course you can factor out the B, and you arrive at this result. Then for the apogee, that occurs at an angle of pi, so putting pi in there you get -1. You put in that A is epsilon B, and we get B times 1 minus epsilon. So if we take the reciprocals of those, r0 plus rf, then it'll be the reciprocal of this, so it's 1 over B, 1 over epsilon plus 1, and this will be 1 over B, 1 over 1 minus epsilon, and then I'll just factor out the 1 over B. I'll put these two over a common denominator, which will be 1 minus epsilon, 1 plus epsilon, or 1 minus epsilon squared, and it'll be 1 minus epsilon, 1 plus epsilon, it'll be 2. Now, cross-multiplying, we arrive at this result right here. Oh, I suppose we need to cross-multiply down the 2. I just need a bit more room here. R naught plus Rf over 2. That, of course, is the A constant. And I've just shown that that's 1 over B times 1 over 1 minus epsilon squared, which proves this result right here. So the reason I need that is I want to argue that A times 1 minus epsilon squared is reciprocal B. So what I'll do there is write the A to the fourth as A cubed, and then I'll have A times 1 minus epsilon squared. And we've just shown through our algebra that A times 1 minus epsilon squared, this thing is reciprocal B. But now reciprocal B becomes H squared over GM. And now, let's just pause that for a moment. Okay, so yeah, I figured out where I was going wrong there. Okay, so first of all, let's clean this out because that's going in the wrong direction. And let's go back to here. This actually is not H cubed, it's actually H squared. I made that a cubed, and that's sort of taking me in the wrong direction. Because, of course, up here it was over H squared. So I just got carried away writing A cubed. So this is H squared. Oh, come on now. Behave. And now what I'm going to do is realize that I've got BH squared here. And BH squared I can replace with GM. So this is going to look a lot better. 4 pi squared, A cubed. And then I replace the BH squared with GM. And that actually is a statement of Kepler's third law because it says that the square of the period is proportional to the cube of the radius. Now it's actually the half semi-major axis length, or the average R value, if you do it for elliptical orbits. For circular orbits, A is just R because R0 and RF are the same. So we summarize then. Kepler's third law says that the square of the period is proportional to the cube of the radius, and then it's 4 pi squared over G times M, where big M is the central mass. So, as a for instance, here's a satellite orbiting the Earth, and it's this far above the Earth at perigee, and it's 4,100 kilometers at apogee. We want to find the orbit equation, the eccentricity, the period, and the speeds near and far. So, give this a try on your own, and then play back my solution. Okay? So pause it, try it, and I will proceed with the solution in a moment here. Okay, so the solution. Well, the first thing to do is to visualize this. So we've got the Earth here, and then at perigee, we're 1,100 kilometers above the surface of the Earth. We're going to have to add the radius of the Earth to that. And then over here, we're 4,100 kilometers above the surface of the Earth. So again, you'll have to add the 6,000 kilometer Earth radius. And again, this picture is not drawn to scale. But there is the orbit. It's a nice elliptical orbit. So the distance of closest approach to perigee is going to be 1,100 plus 6,380 is going to be 7,480 kilometers, and we'll have to convert that to meters. The greatest distance at apogee is 4,100 kilometers plus the radius of the Earth, 6,380. That is 10,480 kilometers. So let's proceed with our analysis. I know that 1 over r is a cos theta plus b. So at an angle of 0, here at perigee, it's going to be 1 over r naught is a times the cos of 0, which is 1 plus b. 1 over rf, this is following what we did on the other page, at apogee, the angle is pi, and the cos of pi is -1. So if I add those two together, the a and minus a disappear, and I get twice b, and I then have to divide by 2, and it's just going to be 1 over r naught plus 1 over rf for the b constant. And so that works out to 1.1455 times 10 to the -7, and this will be in units of reciprocal meters. So I put in these two distances converted to meters. I added an extra 3 powers of 10 there. Okay, then to solve for a, I'm just going to take the b over, and it'll be 1 over r naught minus b. And for the a constant, that works out to 1.9135 times 10 to the -8 reciprocal meters. So I now have the equation for the orbit. It's a cos theta, so 1.913. I'll put the times 10 to the -8 out here. Cos theta plus b at 10 to the -8 power. This is going to be, whoops, what am I doing there? I want to write plus b. I want to write the number in there. Here we go. So it'll be 11.455 times 10 to the -8. So that's the equation for the orbit. Now, we're also asked to find the period. So the period, we'll just take Kepler's third law. Period squared is 4 pi squared over gm times the cube of the semi-major axis, half semi-major axis length, and then we got to take the square root to get the period. Little a, not big A, but little a, remember, is just the average of apogee and perigee, and that works out to 8980 kilometers. Again, you got to multiply by 1,000 to convert it into meters. Big M is the mass of the Earth, 5.98 times 10 to the 24, and G is the gravitational constant, 6.67 times 10 to the -11. When you put all those values in, this should be 8494.5 seconds, or about 2.4 hours for the period. The next thing we're asked to find is the speed at apogee and perigee. Well, to do that, we know the b constant is related to the angular momentum constant, so this will be root of gm over b. So you put in the b constant, the mass of the Earth, and the gravitational field, and you get for your angular momentum constant 5.90 times 10 to the 10, but then the angular momentum constant is rv at apogee and rv at perigee, and then you can solve for those two speeds, and we get 7889 meters per second, and then we get 5630 meters per second. Although we weren't asked to, we can also find the eccentricity, and that works out to be 0.167, so this is slightly elliptical. So that's a Kepler's third law problem. Next, let's talk about the total mechanical energy in orbit. This will be the sum of kinetic and potential, half mv squared, and the potential energy is negative gmm over r. Now the speed in general will have radial and angular components, and those two are perpendicular to each other. So at a given location, this might be the radial speed, and this might be the angular speed. And v, of course, is the resultant of those two. So you can see that its magnitude then, which we're going to substitute in there, is going to be r dot squared, and then r squared theta dot squared, and I'm just going to multiply both of those by half m, and then put the potential energy term here at the end. Now, we want to work on this a little bit, and we want to try and simplify it, and ultimately relate it to the eccentricity. Now, we know what r is, or we know what reciprocal r is. Solving for r, we get this expression here, and we want to time differentiate that now. So, using the quotient rule, we're going to square the bottom, and then we're going to multiply by the derivative of bar. Now, with a minus sign. And the derivative of this is going to be a sine theta, but then because we're doing a d dt, we have to multiply by d theta dt for theta dot. Now, of course, this is simply r, because r is the reciprocal of a equals theta plus b. So this is actually r squared times minus a sine theta theta dot. So r is 1 over a cos theta plus b. This is 1 over a cos theta plus b all squared. But remember that r squared theta dot was an angular momentum constant. So I see r squared theta dot there. And so I get minus a h sine theta r dot. And in a moment I'll put that back in there. Now, using this angular momentum constant, we can look at our other term, r squared theta dot squared. I can write that as r squared theta dot all squared. The reason I'm doing is that this is a constant. But that's going to give me 4 powers of r, so I need to divide by 2 and give me this expression. So why do I do that? Because this is the angular momentum constant. So that is useful. We'll see here. So putting what I've got here in for r dot and what I've got in here for r squared theta dot squared, I arrive at another expression for the total mechanical energy. So it's a half times m times minus ah sine theta all squared plus a half m h squared over r squared minus gmm over r. Now we're making good progress here. I notice that I have 1 over r squared and 1 over r. Well, I know what reciprocal r is. It's a cos theta plus b. So this 1 over r, I'm going to have, replace it with a cos theta plus b. This is r squared, so this is going to be times a cos theta plus b in brackets all squared. So, for my energy then, just let me recopy what I had there. It was a half m, and then it was minus ah sine theta squared. That was my first term. And then I had plus a half m h squared over r squared, and then I had minus gmm over r. Okay, so the 1 over r, I put in a cos theta plus b, that gives me this term. The 1 over r squared, I've got a cos theta plus b all squared. And then I just chose to factor the half m out in front. So that gives me this. Now, a cos theta plus b all squared is going to give me a squared cos squared times h squared. And I choose to put that together here with the sine squared and factor it out. So I had a squared, well, maybe I'll put that in here. This is going to be a squared cos squared. And the a squared cos squared gets factored here and appears there. The next term is going to be twice ab cos theta multiplied by h squared. So that survives here. And then the last term is just going to be h squared b squared. And that survives right there. And then this term is just where it was. Now the reason I bring the cos squared, okay, all this is still times h squared, and then this is times h squared as well. The reason I bring this together with the sine squared, of course, is that sine squared plus cos squared is 1. So I end up with a squared h squared times half m. And here I end up with h squared b squared times half m. Now, with the other terms, I'm going to multiply the half m by the h squared 2ab cos theta. The 2's will cancel, so I get mh squared ab cos theta. And then I'm going to expand these terms, minus gmm a cos theta minus gmm b. But remember what the b constant was, so that gm is h squared times b. So where I have gm here, if I replace it with h squared times b, I see that these two terms are just going to cancel each other out. They're algebraically equivalent. So now for my energy, I've got a half mh squared. I've got a squared plus b squared. And I've got minus gmh m little n. Now we're making progress, but we're not quite there yet, because of course I can once again put this in for gm right here, and that's going to clean things up a little bit. When I do that, of course, gm here, this is h squared times b, so I'm going to get h squared times b squared times m. But of course I had a half m h squared b squared here, so what I end up with is a half m h squared a squared. Then I've got a half m h squared b squared minus m h squared b squared. And a half minus 1 is just negative a half. So that gives me this term here after I factor it out. I substitute in that a is epsilon b. And then I factor out the b, squared rather. But of course, b is gm over h squared. So then I square that. So I get g squared m squared over h to the fourth, cancel off 2 powers of 10, and I arrive at this result for the total energy in orbit. Now then, here we see that that total energy depends on the eccentricity, and also depends on the angular momentum constant. So this is just a nice formulation for total energy. Okay, so remember that we related the eccentricity to the shape of the conic section. So if I take this result that I got, it's 1/2 m gm over h squared, sorry, g squared m squared over h squared times eccentricity squared minus 1. If the eccentricity is 0, you can see that the energy is negative for a circle. Okay? If the eccentricity is 1, then for a parabola, the energy is exactly 0. For an eccentricity greater than 1, the energy is positive. The energy is still negative for an ellipse, but with an eccentricity being bigger than 0, this is actually going to be slightly greater than the minimum energy of that circular orbit. So this just means that an elliptical orbit has more energy than the circle does. Now this negative, negative 0 and positive ends up being quite interesting because we can relate the orbit to a potential well. Now the way we do that is by going back to our expression for the total energy, and then once again taking that second term and writing it as h squared over r squared. I guess we'll just go through the algebra here again. So if you square this over r squared, then you get exactly r squared theta dot squared, as we showed earlier. So I can replace the r squared theta dot squared with h squared over r squared. Okay? And so now, this is kind of like a kinetic energy in the variable r. And I'll put that in quotes, because obviously the real kinetic energy includes an angular term as well. And this is kind of like a quasi-potential energy in the variable r as well. And so we can make a graph of this potential energy function and then examine the motion as a potential well. So this is a potential energy that looks something like constant over r squared minus another constant over r. That was supposed to be a c, by the way. And, you know, those c constants, well, they're related to the masses and things like that. The value is not that important, so let's just take some typical values and plot this function, see what it looks like. Well, you get something that looks like that. That's a potential well. And so when we said the energy of the circle was a minimum, this is exactly what we mean. It's right down there. If you have slightly more energy, say if this was your energy level, then you have an ellipse with two different values of radius. This would be the greater distance, this would be the smaller distance at perigee. Okay, so that would be an ellipse. And as you keep increasing the energy, if you get to an energy of 0 right here, that has escaped. That's a parabolic orbit. And then way up here, this is a hyperbolic orbit. It's an energy that's positive. So this would be a circle. And it just stays at 1r value. Here, if you add a bit more energy, if you add a bit more kinetic energy, then you're going to boost into an elliptical orbit, and these two will be your turning points, 1r naught, 1rf. If you keep adding energy and you reach the escape point, then this is a parabolic orbit. So this is a really nice visual for the orbit and the conic section and the eccentricity and how it all relates to the energy. So what we've got next is a problem, kind of like what we just talked about. We'll start with a circular orbit, and then we'll boost the speed by 10%. And we'll work out the kinetic and potential and total energies, find the angular momentum constant, get the eccentricity. And the answers are all given here, so you should be able to work your way through this. And then here, when you've done this, plug the values into this expression and show that you get the same as this energy right here. Now those are gigajoules, that's 10 to the power of 9. All right, so give this one a try, and we'll talk about this one to start our next class.